Log on, tune in, find out. Another good idea from Cambridge.
Okay, so first I would like to thank the organizers for the invitation. It's my first time here, and it's a wonderful setup, and the meeting so far has been very interesting. Since I'm talking about CT, let me start with an interesting story which happened last week. Actually, we had a little bit smaller scale of medical imaging conference in Shanghai. Quite a few people here were there, and also most of you probably know Stanley Osher, who is a die-hard fan for image processing, invent the total variation for image processing and so on and so forth. Unfortunately, he was tripped during the conference and get a cut. He was afraid of broke his jaws, so he went to the hospital. When he came back, the first thing he told me is, he looked at the CT X-ray he took. He's amazed how clear it is. He thinks there's nothing we can do to improve it. Okay, so that's med challenge, not a med challenge. But of course, that's a very special situation. You sit still. CT is perfect for imaging this structure, damage, and all these things. But there are many other challenges. For example, if you don't want to look at just structures, you want to look at other information, functional information, and you have to invent other more sophisticated imaging modality. Or this 4D CT is basically mainly used for lung cancer treatment, where people breathe, you cannot stand still, and you may have to take at different times. So there's kind of motion, deformation, changes, and so on and so forth. And if your CT speed is not enough, like for cone beam CT, just like when you take a camera, when your speed is not very fast compared to the motion, you have blurring, you have other complications. So here we're trying to apply some recent development in information science or image analysis to 4D computed tomography, especially address the 4D means in order to capture the motion, in order to get treatment plan dynamically depending on time. So you need another dimension, which is time, like videos. Of course, it doesn't. This is much more complicated process. You cannot have as high as resolution as we usually shoot for video. So this is 4D computed tomography, and this is a joint work with my previous student Hao Gao, who is now at UCLA, Jianfeng Cai, who is now at Iowa, and Zhou Weishen at National University of Singapore. Okay, so our motivation is the following. We want to develop a model for spatial and temporal formulation using matrix model, so that explore maximum temporal coherence of spatial structure among different phases. Okay, so the reason is if when you take this 4D CT, you're taking picture on about the same body in about the same area. So there are a lot of coherence in space and time, and hopefully, if you can utilize that, you can improve the image quality, like remove the blurring, the noise, detect the motion and changes. So basically, one of the treatment plan for this lung cancer is your treatment plan has to depend on the motion, so that you can deliver the radiation into the right place. That's why you need CT images all the time. And also many times you want to track or see how the treatment is taking effect, how the tumor changes, or so on and so forth. And sometimes this is due to relatively low contrast. These changes are not so easy to detect. Of course, the ultimate thing is if we can utilize, we're basically looking about similar situations. An extreme situation is if every time you're just taking the picture of the same structure, stationary, then you don't have to take so many pictures. So hopefully if you can explore this coherence, both temporal and spatial, you can reduce the measurement, or which means equivalent to reduce the radiation dose. So hopefully that's the ultimate goal, but you still get a similar quality images. Or you have the similar, with the same measurement, you get better image quality. So that's the motivation. The key point is, okay, so I will mention a few current models for taking into account both spatial and the temporal coherence, but most of them are quite local. If you're talking about total variation or derivative based, so that's basically taking coherence both local in space and local in time. So, but here we try using a matrix formulation to take the maximum coherences among all time. Okay, so the basic idea is you put each image as a column of a matrix, and then you try to decompose the matrix in low rank, which corresponding to the common part, or most common part during different phases, different time. If you're just shooting at the stationary part, the rank should be just 1. If you have slowly changing, the rank should be still low relatively to the frame you take. And sparse part, so basically if there's things moving and also things changing, that should come to this part. The last things is the noise, because always there's noise. Of course, you can add other things into this. I will see if you have more complicated model, you may add some deformation component here, so on and so forth. I will discuss that later. Also, based on this idea of taking advantage of coherence in time, so we really tried to do this in experiments, but that's much harder for mathematicians to do. So we developed a dynamic scanning strategy that basically utilize this coherence in time. So basically, not every time you have to look very carefully with a lot of measurement, but you look at different things at different time. But if you fuse this information together, hopefully you take advantage of the redundancy, coherence. You don't need that measurement, but you still can, because a lot of this measurement is, if you shoot the beams inside, most of them is interacting with the background. So you're looking at the same background most of the time. So you hopefully reduce that dose, you still can recover the common or stationary background. Okay, so I'll tell you what that is a little bit later. Okay, so this is the formulation. So this is a big, huge matrix, because each column is 256 by 256 long if you have a 256 by 256 images. And this is the time, how many frames you take. This is a large matrix. So the thing here, the coherence is not in the measurement. The coherence is the underlying ground truth. So unlike, I guess, the first talk of today, so my coherence is in the x, okay? And this x, which is on the underground truth, after redundant transform, X-ray transform, you get a measurement. Especially due to our later dynamic scanning procedure, this transform may be different. Okay, they're not the same A for different time. They're different. So basic coherence is here, and the measurement here, and with the noise. So we want to decompose this one in the not measurement domain, but the real physical domain into this matrix decomposition. Okay, so that's the point. So it's basically say my X is now again that big matrix. Want to decompose into here. Currently just 3 parts. The first part is the low rank, which is corresponding to the common background, stationary background part. X2 is the sparse part, which is change or motion or things like that. And the noise, which is both incoherent both in time and space. Okay, so this may be incoherent in time, but should be relative coherence in space. Okay, so decompose into 3, and way to do this, a little bit relaxed, because instead of low rank, you're really counting how many non-zero singular values, or sparse, counting how many non-zero elements. You're replaced by the nuclear norm, you're replaced by the L1 norm. That's really a lot of things has been done recently in compressive sensing and matrix decomposition work. So this is part is noise. We assume it's Gaussian noise, so we're using the standard L2. We think this is a low rank part. We're using nuclear norm. Okay, so again, the sparsity is very interesting. So actually, I would see in general, these two parts is highly non-trivial in different applications. A lot of depend on the prior knowledge. But the good thing about medical imaging is you do have a lot of prior knowledge. So the question is whether this is relevant, right? I was saying it's quite insufficient in many real applications. And also here, many times you just say sparse in X2, which means what? Means just a function is sparse. Okay, here we do the sparsity is enforced in the wavelet or framelet transform domain. So in a sense, the sparsity could be, I will show you, it's not just function sparse. If the function sparse, so basically this part captures just like isolated dots. Okay. But we want to capture maybe a moving object, which is piecewise constant, so which means sparse in the gradient norm, like TV, or it could piecewise linear, could piecewise smooth, which means like high order TV, so the second derivative may be sparse, and so on and so forth. So using this, I'll show you what this transform is. Actually, you can have capture sparsity in all those possible scenario. Okay, so and this is quite straightforward, just using nuclear norm to model the low rank structure. Okay, so this dynamic scanning procedure here is what we propose. So this is the full view. Okay, so basically at different frame, different phases, you're shooting your projection. You have the same setup. You're shooting at the same direction, measure at the same places, projection in the same directions. So every time you use the same scenario. Okay, partial views. Okay, so a simple, straightforward partial view is nothing. It's just you subsampling. Instead of using this so many measurement, you're just using a subset of this doing the measurement. Okay, of course this is worse than this. This is kind of subsampling of this. The dynamic view is like this: is you're at a different time, you are using different of this measurement. Okay, so at phase 1, you use maybe 1, 4, 8, 1, 5, 9, 14, and so on and so forth. The other one is phase 2, you're using 2, 6, 10, something like that. Okay, every time you look a little bit different view, so which means in general you look the whole structure from everywhere, like this full set, but at different time you're looking only using subset of these views. But you want to use coherence to get a reconstruction or information images almost as good as look at through all this. I think this also, you know, when we have the same I took the same taxi here with Li Hong. So maybe there are other ways doing this partial view for these optical things could be aligned. If you measure the different views, the question is how to fuse them together. So this could, I think there could be some interesting things using this. Each one is a partial view, but you fuse them together using some kind of, but there's some alignment. I will tell you some alignment we propose. Okay, so this is basically application and our model. So here is some details about what we do. So first of all, our sparsity is not enforced just like in the function space itself. So basically in the transform domain, so in our case, it's represented by tight frame. The tight frame is a kind of multi-resolution framework, but it's different from orthogonal basis usual wavelet transform in the sense it has redundancy. So redundancy is very important when you have missing information or noise because it's very robust. If one of the coefficient of the orthogonal basis is lost, there's no way you can recover it. But if you have redundancy, even you corrupted or lost some of them, you lose some of them, you can still recover it. And also it has a very easy decomposition and synthesis operation. So basically this W is a very tall matrix. Each one you operate it on a function is a decomposition into the basis. When you synthesis, again, it's very easy. You just transpose this and multiply those coefficients, that's it. So that's this. It has left inverse, but it doesn't have right inverse because of long matrix. Okay, so in our particular case, our framelit transform, it is composed of this kind of low pass filter. This is nothing like averaging. Okay, high pass filter, if you look at these two, one is the center difference for first derivative. So this is something like total variation, already included in our sparsity things. Also could be sparsity in this, which is second order central difference for the second derivative. So which means if your second derivative is sparse, you can also capture that. Okay, so that's
in time or in space?
In space. In space. Time is in the low rank. Low rank is the finding the coherence kind of regularization, but it's not like TV in time, which is local between consecutive ones. It's a global one, okay, using low rank. Okay, so now it's looks quite formidable optimization problem, but it's not so formidable. First of all, it's convex. Okay, so has been relaxed from those counting this NP hard problem, counting how many non-zero singular values, how many non-zero in this matrix, how many non-zero element, number of non-zero element, all relaxed to some convex norm and so on and so forth. So, but still the difficulty is compared to some previous model, which I'm going to talk about a little bit later, is we have a mixing matrix or transform matrix. We have, this is this X-ray transform. So basically mapping the physical domain to the measurement domain, and this is transform domain. So basically all these things mixing different components together, so it's non-separable. Okay, so the key point is the difficulty is non-smooth because this is like the L1 things. It's not too bad, non-smooth only at the origin, and otherwise it's almost linear. So in a sense, non-smoothness, before people dealt it with other method, always try to smooth these things, but here there are a lot of recent development telling you this is not very formidable, but non-separable is actually makes things a little bit harder. So the key point is you want to reduce such a problem to a series of easy sub-problem, which you have very simple ways to optimize or to solve. I think the first speaker today talked about that too. You see some very familiar formulas or name terminologies. So basically, the crucial thing is if it's separable, although it's problem like this, L2 norm, Frobenius norm of a matrix, so this is all matrix, plus L1, this is very simple. You can do a simple shrinkage, okay? You can explicitly write out, because you can write out component-wise, and each component, one component has nothing to do with other component because it's all separable, just sum of each component things. And a quadratic plus absolute value is very easy to do by this simple shrinkage. Even for this nucleus norm with Frobenius norm or L2 norm, it's also very easy. You just do singular value thresholding. To do this, the most cost part, you have to do singular value decomposition. And then after doing that, you just thresholding the singular values, retain those singular values bigger than tau, and replace the other by 0, and that's what the matrix minimize this. Of course, there's again recent advances. You don't have to do full SVD. You can try to do things without fully do SVD. Okay, so they're fast algorithm. But here we use this, but each of this is very simple. The main thing is how you reduce the non-separable problem, because this is all separable. There's no mixing matrix and in here or here, so that's the key differences between this simple problem to the previous problem. So this idea was mainly proposed in this split fragment, or there's augmented earlier on in optimization community, augmented Lagrangian. It's basically introduce new immediate variables so that anytime you don't mixing the optimization of AX with X. So basically, so in this case, after you replace this, okay, so they're only mixing in the first term, but that's quadratic. Everything else, okay, so basically, if you look at and also you're kind of alternating, minimizing in different variables. When you do x1, so when you doing the d1, okay, after introduce this, the d1 is not mixed by this a, it only appears here, and also this d1, I think this is the nuclear norm. And the same things when you introduce d2, when you do, you don't mixing with this ax2, you have this. So this is kind of these split fragment approaches by introducing these new variables. Then each of these things, okay, this is next thing is, each of these things can be done, the second step here, can be done simply by singular value thresholding, which is very simple operation. The third one is by shrinkage. It's also very simple. The first one is a quadratic things, so it's quite easy to do because they are all quadratic things. So it becomes much cheaper things. Of course, each operation is cheaper, but then you have to do many iterations. But hopefully, you don't have to do many iterations. Okay, so related work. So the related work, I think in the medical imaging community, people already tried different ways of doing this 4D CT. So basically say this is the fidelity term which match your measurement. This is regularization in space, could be TV, could be other regularization. The regularization in time, but as I said, both these are local operation in time and space. So you don't take global coherence in your, especially your bracing is periodic. After it takes a long time, many of the things come back. Although in time they're not very close, but really they're looking at very similar things, even they are very far away in time. There are now very recent work by people, a group of people in San Diego. They do some non-local means to looking at patches in space and time that look similar and using them to do the denoising and so on and so forth. Of course, the most relevant thing is related to robust PCE for video face recognition work done by these people. Of course, the main thing is their work is based on this low rank but plus sparse decomposition. So the problem is the following, is if you have a matrix M, okay, and this matrix M is low rank. Sorry, you don't observe the the matrix M itself, but you know there's a low rank matrix, and a small set of its element or entry are perturbed by some sparse matrix. So basically some element is changed, but the change is sparse in the location. So if you, this is what you observe, the D, the superposition of low rank plus sparse, if you only measure or sample part of this sum matrix, can you recover both of them? Okay, so in this work, they propose this convex relaxation optimization, which is under certain assumption, which in practice again that's difficult to check and most of the time is not satisfied, is incoherence of the singular values with the coordinate basis, which is not transform invariant, but they require that. your singular value should not be too close to this your coordinate vector. Also, the element you sample shouldn't be randomly sampled. If you have that, they have some theory about how good, what's the chances if you do this, you can recover this M and S0. So our differences here is decomposition is in the measurement is not in the image domain or measurement domain. It's in the physical domain. So there's a matrix through that transform, and this A is this X-ray transform is quite ill-conditioned. Definitely those incoherent things is not easy to satisfy. Sparsity is not enforced is enforced in transform domain. So in this case, if you just do the sparsity on the X2, what you can have in that part is just isolated dots. Okay, not like piecewise constant or any moving object. Okay, so in transform domain, and also really what we hope is this methodology doing this image kind of analysis of fusion can have some practical use by using this dynamic scanning. You can reduce the radiation dose. Okay, so let's look at some example. Of course, none of them is real data. It's on phantom data. But we're trying to get real data, especially cone beam data, try this kind of methodology. So one is basically, let me show you. Well, the problem is always, it looks very clear in the screen, but it's not that clear in this. But I have to admit it's much better than the projector we used in last week. So basically, this is the true ground truth. Okay, so it's superposed about this stationary background. Okay, stationary background plus some this elliptical object is moving. Okay, they're not just fixed location. They're moving. There are two little dots moving. The contrast of the big circle here is changing. And so on and so forth. There's motion of these two little things, motion of these big two elliptic optic things, optic shapes, and also the intensity change of this big circle. So basically, if you look at a different time, so it's this one stationary background plus these differences, changes. Okay, so this is the real images. And if we do our models, so of course, this decomposition is highly ill-posed, right? There's many ways you can decompose. You cannot have the perfect one, but you already see this is our reconstruct. This is basically, if you look at the denoised image, this is our denoised image, okay? This is basically x1 plus x2. There's noise is the differences between x1 plus x2 with the true true ground truth. This is, you see, if you want to look at the denoised image, this is this. If you look at the low rank part, that's the low rank part. If you want to look at the change, intensity change, motion, and so on and so forth, it's basically, especially intensity change is captured here. The motion, of course, the motion, as I said, you can basically, it's part of it can go to the sparsity part. The symmetric differences could go to the sparse part. The common part, because the motion is slow, many part appears in many different phases. So that could be part into the common background. So this decomposition is definitely, although you know the background, you know the ground truth, but this decomposition, this whole problem is ill-posed. So you definitely see there's some motion of these two elliptic things, because this is capture the kind of differences between different phases. And you see the intensity change, and also you see little two dots due to the motion. And this is if you using the regularization in space by in space in the gradient, not total variation, but H1 norm, gradient square. This is your TV in space, but no time regularization. This is TV in space and time. This is just the noise image. I didn't, in the paper we also show this decomposition, but you see the best part, of course, the TV1, it's, we give quantitative measurement of the differences, and this is our low rank plus tight frame decomposition, and this is error, and you see our error is the smallest. Okay, phantom 2. Okay, let's see, this is phantom 1, that's the error, and phantom 2, you see where our is even better. So this is the following situation where even your human eyes even look at the computer screen, you can now see the changes or detection the motions. So basically this is some MRI images. On top of this, we put two elliptical shape like the previous one, but very low contrast. It's very hard for you to see on the image there are two elliptical shapes. Okay, they're moving too, and so basically this plus this is equal to this. Your human eyes cannot see there's something there, changes or motion. But if you do our method, you will see immediately, you see that. Of course, it's again cannot get a perfect decomposition, but you do see the little things coming out. Okay, so which means something you cannot see even by eyes. You see there's some object there and they're moving and so on and so forth. Okay, so if you look at the error here, so our error is much smaller than all the other methods. Okay, this is our model. This is others. Oh, sorry. Okay, so this is our motion detection. Okay, this is our method. You can see the motion. So the next thing is we try to compare. You have full view, full measurement, or you have partial view, only subsampling, or dynamic view. Our goal is the dynamic view, which has the same number of radiation dose. Actually, expert learn from expert. Although the CT is helped to do the radiology therapy, but the radiation dose is almost 40% of the whole doses you use for this therapy. So it's very important to reduce the dose. So here, hopefully, we can see using the dynamic scanning procedure, you can see almost as clear as the full measurement, but use the dose is equivalent to the partial views. Again, this one is we see using our the full view. This is what you saw just in the similar as the previous page, and this is what we do. You do see the motion or the change and so on and so forth. And if you look at partial view, the results are definitely much worse. If you look at the dynamic view, okay, which is just you are measuring subsampling, but at the different directions, though they're basically only 432 projection. The full view is 256 projection, only 1/8 of the projection. You see you have pretty good result, and quantitatively this is basically comparison, full, partial, and this is dynamic view. So this first and last column is very similar. Okay, if you look the errors, partial view is this much error, dynamic is this error, and this is this much error. Okay. Okay, so again, the question is the main things about the practicality of this model. There are two things: low rank, big assumption, sparsity. Low rank is not a bad thing, but if you think the way you put all the images pixel by pixel, align them just in that, any little shift, any little dilation, translation, or even intensity change could cause it's not low rank. Okay, but structurally it's low rank, but many small perturbation because you just line images using the indices, RASC, this range. So the main thing is how do you make the low rank assumption more valid in more general situation. The other one is in what domain you should enforce the sparsity. Again, that's very application problem dependent. So this I don't want to talk too much, but say one thing is saying you your body is not stationary. Okay, you breathe, especially for lung, it's breathing, it's moving. So there are no strictly stationary part. So but on the other hand, you can see there's some after some deformation, one can register to the other. So the main thing is, can you also try to find some appropriate deformation or registration? After that registration or deformation, the low rank is more valid. So basically, you say, okay, assume your measurement. So this is people already done that in video. Basically, this is instead of the true image, ground truth, every pixel is moved a little bit. So now the question is, if this deformation field is small, you can do linear approximation of this, and then everything still become convex. Of course, you try to find another big component, big matrix, which is a deformation field, such that after this deformation, linear approximation of the deformation, the remaining, the x1 still low rank, this is still sparse, and this is so on and so forth. Okay, so these things. But in our application, there's also more complex complexity, because we do not do that in the measurement domain. It's really there's another composed with another X-ray transform. Okay, so if I assume everything is fine, I can take left inverse and then move this TI to all the measurements. Basically, say hopefully all the things, the deformation field, everything, it can be recovered from the measurement data. That's the whole point. So you move everything to the measurement you have, and you still do this, you can do this. Okay, but the big assumption is I have left inverse. Okay, so X-ray, or most of the time again, is the long matrix is underdetermined. So AI does not have not only mixing, but it also does have not left inverse. More ill-posed. If you think, the good thing is this: if you add more and more decomposition or more factor, the model can be more and more general. But something you have to pay, the problem becomes more and more ill-posed. Basically, if I have some object moving in these images, I can find some way to put into the sparse part. I also can find some way to put into the deformation part. So which in which, you don't know. Okay, so there may be much more ambiguity or more ill-posedness in this. And of course, all this failed down if you have a large deformation, which you cannot linearize. Okay, so these are the challenges. So one, then you try to go back to try to improve the model, but also, again, I said for medical imaging, hopefully there are many prior knowledge you can use. Hopefully, that's a very general model. You assume the deformation can be arbitrary, but many things is not arbitrary. For example, if you take an X-ray today, you take an X-ray tomorrow, maybe this misalignment is due to some rigid motion. You put in the different locations. So rigid motion, or also the deformation field. Many people assume that the tissue is somehow incompressible in some way, and you give more and more constraint. That makes the problem a little bit better posed. But for rigid motion, the main thing is reduce the dimension, degree of freedom. But on the other hand, then the problem cannot be non-convex, but it's much a smaller non-convex problem. Knowledge-based decomposition, and basically say if your beam, okay, so the resolution is very much dependent on your projection direction. So if I know I'm really shooting the beam in this direction, then I know in what region, in which direction my data are more accurate than other things. So I can put a weight to saying, okay, what measurement in what region or in what direction are more trustable than the other. So you can put in this weight, so then you can fully, otherwise this is mainly say depends on what happens most, and many times if your good image has a corruption, or sorry, if you're a bad, you have too many bad images and pixels, and that bad pixels will affect the outcome. So you construct some knowledge-based weighting matrix. And also, so time is almost up. Here we explored time coherence most of the time, but we don't impose any spatial coherence. So for example, if you don't have measurement at 1 pixels in all phases, you have no way to recover it because there's no information there. But you can look at the spatial coherence, like in painting, to do that. So the thing is, which you can have another term, is regularization or some regularization on each column of X1, the reconstruct image. That basically take specifically spatial coherence. Okay, so that we're going to do. So our work is mainly reported in this recent work, published in this Physics in Medicine and Biology. And also, let me do, since I have done some optical imaging, and also we developed some fast solver for RTE, the best way to test whether it's good or not, to ask people to try it. So if you want to solve RTE, which is not a trivial job, you're welcome to use our developed code, which is here. Okay, thank you for your attention.
Questions, please?
This is very interesting work. I'm not so sure what is the clinical setting you are targeting though. I mean, are you targeting radiation therapy? I mean, that's one question. The second question is that it seems that you have to inverse or do singular value decomposition on huge matrices, and this takes forever. Even
actually, there's now very efficient algorithm. Yeah, SVD. You know, now linear algebra is revisualized after Google search engine. It's all about doing this SVD and also a lot of these things. Now you are quite amazed how large matrix they can do singular value. But also there are fast algorithms doing without explicit, with approximate singular value decomposition.
How about the clinical setting?
Clinical setting, so there are two. The simplest one is this. People do, you know, they take 4D CTs of your body, and your breathing has a cycles. And so they basically, I know that, well, at least I visited one hospital where they put each CT scan, they divided the whole breathing cycle, which is 4 to 6 seconds, into 10 to 12 phases. And they put each CT things into each phases, and then they do image processing among all these images in the same bin, phase bin, and do these things. So our is basically saying automatically doing that, and also the other thing is to improve the image quality. The other thing is, of course, is also saying, can we get similar image quality by taking much fewer measurements? So basically, like cone beam CT, in order to have enough images in each phase, they have to take 4 minutes. Okay, but maybe after take 1 minute, there's already a few things enough using our maximum coherence. Take this 1 minute should make after 1 minute of the scanning, you can get similar quality images as those taking 4 minutes.
And how is this different from dynamic CT? Means
oh, this is basically actually the cone beam CT is like that. It's changing all the viewing angles at a different time. Okay.
And I have another question. I can.
Just a short one.
Yeah, I mean, you are mixing domains, right? So, which is, you are mixing domains.
Which mixing?
You are mixing the domains. It means you are doing reconstruction, and you also looking on the Fourier space.
Oh, the wavelength transform domain. So basically, my sparsity is enforced there.
And this is why you didn't try to do everything, for example, on one space. And why you
TV. So basically, TV. Okay, you use just TV of that. You only look at sparsity of gradient. It cannot look solution is sparse. It penalized solution is sparse. It also doesn't look for sparsity if it's in second derivative sparse. Okay. So in this, it's basically the L1 norm on those coefficients. Those coefficients have averaging, having first divided difference and second divided difference. Anything sparse in that can be captured by this. So if your image has piecewise constant, it can be included. If its image is just sparse, it can be captured. If the image is piecewise in second derivative it's sparse, then it's also.
No, my question is why you don't try to reconstruct.
Sorry, I think we should continue. Please ask if you have a break. Thank you very much.
Okay.
We need to go to the next.